We're in section 8-2, and as we recall, we have some function f of x, which is a summation n equals 0 to infinity a n x to the n, and we have some initial condition. So we'll take initial conditions and we'll say f at 0 is 2, and f prime at 0 is 2, and f double prime at 0 is 2. And then we ask ourselves, well, what does that mean? Well, if we look at the function f of x and we say, well, that's a0 plus a1x plus a2x squared plus a3x cubed plus, keep on going forever. And we say, well, f at 0 is going to be a0, which has to be 2, which implies that a0 is 2. And then we look at f prime x, and we say, well, that's going to be a1 plus 2a2x plus a3x squared plus blah, 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 blah. And we say, well, f prime at 0 is 2, so that implies that a1 is equal to 2. And then we look at f double prime x, and we see that that's 2a2 plus, what is it, 6x plus whatever. And then f double prime at 0 is 2, which is equal to 2a2, which implies that a2 is equal to 1. So when we have initial conditions, we would like them to be at 0, because that tells us what our a0, a1, and a2 might be. And if they're not at 0, then they're totally useless. So if I had an initial condition, f prime at 4 is equal to 7, well, that's not going to do me much good. But if I have initial conditions at 0, they're going to do me a lot of good. Okay. We're going to look at problem number 16, and this is a section 8-1 number 16. And we say 2xy prime is equal to y. So 2x summation n equal to 1 to infinity n a n x to the n minus 1 minus summation n equals 0 to infinity a n x to the n is 0. We bring in the 2x to the inside of the summation sign, summation n equal 1 to infinity 2 a n x to the n minus summation n equals 0 to infinity a n x to the n is equal to 0. We remove the n equal to 0 term so that we can have a summation n equal 1. So n equal to 0, that's going to be a minus a0 plus summation n equal 1 to infinity 2an minus an x to the n is equal to 0. And we can rewrite that minus a0 plus summation n equal 1 to infinity a n x to the n is equal to 0. And we say, well, isn't that convenient? Well, what does that mean? Well, that means that minus a0 has to be 0. My recurring formula is an is equal to 0. So my answer is an is equal to 0 for all n. Yeah, that's called a trivial solution. The method has failed. Method failed. So there's no guarantee that I'm going to get a solution using a power series method. So isn't that lovely? Just what we needed to know. Now we're going to work a problem, another problem from section 8-1, and it's going to be number 21, I think. I think it's number 21. You'll have to look in the book and find out. Y double prime minus 2y prime plus y is equal to 0. Now normally the odd number problems you guys work, I work even ones. So obviously somebody has asked me to do this in class. So y0 is 0, y prime at 0 is 1, which implies a0 is 0 and a1 is 1. So we'll remember those initial conditions. We have summation n equal 2 to infinity n minus 1 a n x to the n minus 2, that's y double prime, minus, and we'll bring the 2 in, 2 n a n x to the n minus 1 n equal 1 to infinity plus summation n equals 0 to infinity a n x to the n is supposed to be 0. Okay, so we'll do a substitution, and we'll substitute n is equal to n plus 2, and we'll do a substitution in this summation, n is equal to n plus 1, and then everything will be the same index. So I got summation n equals 0 to infinity, n plus 2, n plus 1, a n plus 2, x to the n, minus summation n equals 0 to infinity, 2 n plus 1, a n plus 1, x to the n, plus summation n equals 0 to infinity, a n x to the n is equal to 0. Okay, now I got my indexing right, so I can go and put everything in one summation sign. Summation n equals 0 to infinity, brackets, n plus 1, n plus 2, n plus 2, n plus 1, a n plus 2, minus 2, n plus 1, a n plus 1, plus a n, close brackets, x to the n is equal to 0. Now, from my initial conditions, I remember that a0 is equal to 0, and a1 is equal to 1. I have a recurring formula. Sitting right here, I have a recurring formula. I'll circle it in blue. And it says that a n plus 2 is equal to 2 n plus 1 a n plus 1 minus a n divided by n plus 2 n plus 1. And for all n equals 0 to infinity, greater than or equal to 0. Well, that was pretty bad, wasn't it? All n greater than or equal to 0. Okay, so I put in my first n is equal to 0, and I get a2. And a2 is equal to 2 times 1, a1, which is a 1, minus a0, which is a 0, divided by 3 times 2. No, 2 times 3. No, 2 times 1. 2 times 1. Okay, so I got 2 1 times 1 minus 0 divided, so I get a 1. a2 is equal to 1. Okay, and then I go look at n is equal to 1, and I get an n3. 2 times 2 times 1, because A2 is 1, minus A1, which is 1, divided by 3 times 2. Okay, so I've got 2 times 2 is 4, minus 1 is 3. 3 divided by 6 is 1/2. Okay, and then I need to see my recurring formula to know what I'm doing. And I have n is equal to 2. I'm looking for A4. So A4 is going to be 2 times 3 times A3, which is 1/2, minus A2, which is 1, divided by 4 times 3. 4 times 3. Okay, so I got 3 minus 1 is 2. 2 into 12 is 1/6. So I got a 1/6. Okay, I'm going to do it one more time, but I'm going to memorize my recurring formula so I can do it. N is equal to 3. I have A5 is equal to 2 times 4 times 1 over 6 minus 1 over 2 divided by 5 times 4. And let's see, 6, 3, I have 4/3 minus 1/2. I think it's 1 over 24. Let's hope that's right. So when I get done, I have that for a final answer. Final answer, y of x is going to be x. First of all, there's no A0, so that's 0. So I got x plus x squared plus 1/2 x cubed plus 1/6 x to the 4th plus 1/24 x to the 5th. And we're going to want to check our work. So we will check our work. And y prime is going to be 2x plus 3/2 x squared plus 2/3 x cubed plus 5/24 x to the 4th. Y double prime is going to be 2 plus 3x plus 2x squared plus 5 over 6x cubed. Okay, and what do I want? I want one of those guys minus 2 of them, and one of these guys, and when I get done, I want it to be 0. Okay. Where did my 2 go? Oh, I forgot something. I'm sure everybody saw it. There's a 1 plus, so the x becomes a 1, and the x squared becomes a 2x. Okay, so that's good. So I've got minus 2 plus 2. Those guys go away, 0. I've got minus 4 plus 1 plus 3 for a plus 4, so that guy goes away. I've got minus 3 plus 3, so the x squared term goes away. I've got 1/2, I've got 4/3, and I have 5/6. So I got minus 4/3, 5/6, and 1/2. Does that go away? Okay, Okay, so 1/3 is 3, 6, 8, 6, 4/3 minus 4/3. They go away, and my answer checks. How totally convenient. Okay, now we're going to look at something slightly different, and we're going to say we've got some formula that's ax, where a of x is just a function of x only, y prime plus bx, where bx is a function of y only, plus cx, which is a function of x only, is equal to 0. I'm going to rewrite the formula and say that's a row of x is bx over ax, and q of x is cx over ax, and we'll change this to a p. That's going to be a p. Y double prime plus px y prime plus qx y is equal to 0. So that's the function we have. And the issue is, are p and q analytic at x is equal to a? Are p of x and q of x analytic at x is equal to a? Now, if they are, then that's wonderful. That implies we have an ordinary point. How ordinary? Ordinary point. And so that's kind of cute. But what if they're not? What if something happens and p of x ends up being 1 over x, and x happens to be 0, and now I'm not analytic? So if that's the case, then I don't have and x is equal to 0 is not an ordinary point. Okay, and clearly we're doing that because in section 8-3 we're going to look at ordinary. We're going to look at regular singular points and irregular singular points. So in 8-2 we have to discuss ordinary points. Yes, I know, isn't that wonderful? Okay, we're in the 8-2 section of the book, and we're doing problem number 2. And these problems look extremely like the section 8-1 problems. So I've got x squared plus 2 y double prime plus 4xy prime is equal to 2y is equal to 0. And I do that, and I look at that and I say, well, if I put that in the form y double prime plus px y prime plus qx y, and I ask myself, do I have a singular point at x equals 0? The answer is no. So at x equals 0 I have an ordinary point. Isn't that lovely? And we'll worry about why I worry about that later. But if you remember we'll talk about that. If you remember that I have y of x in the Taylor expansion, summation n equals 0 to infinity, a n x of n, I'm expanding this around x is equal to 0. That's how my expansion is being expanded. So if x is equal to 0 is a singular point, then I have problems. Well, I don't have problems yet, so I'll just solve this guy. So I've got x squared summation n equal 2 to infinity, n minus 1, a n x to the n minus 2, plus 2 summation n equal 2 to infinity, n minus 1, a n x n minus 2, plus 4x summation n equal 1 to infinity n an x to the n minus 1 plus 2 summation n equals 0 to infinity an x to the n is equal to 0. Okay, so I'm going to bring in the x squared, I'm going to bring in the 2, the 4x and the 2, and end up with summation n is equal 2 to infinity n minus 1 an x to the n plus summation n is equal 2 to infinity 2 n minus 1 an x to the n minus 2 plus summation n equal 1 to infinity 4 n an x to the n plus summation n equals 0 to infinity 2 an x to the n is equal to 0. Okay, I got to do something. I have x to the n minus 2, x to the n, x to the n. So in this guy, I'm going to do a substitution. N is equal to n plus 2. That way I get everything x to the n. Okay? And I'm going to try to do the substitution in, well, I'm not going to. I'm going to rewrite everything. Summation, and I don't want to be in that color though. Summation n equal 2 to infinity n minus 1 an x to the n. Summation n equal 0 to infinity 2 n plus 2 n plus 1 n plus 2 x to the n plus summation n equal 1 to infinity 4n x to the n an x to the n plus summation n equals 0 to infinity 2an x to the n is equal to 0. Okay, so I look at that and I say, well, I have to remove the n is equal to 0 and the n is equal to 1 term. Out of that summation, I have to remove the n is equal to 1 term out of him and remove the n is equal to 0 and the n is equal to 1 term out of him. And when I get done, I'm going to have summation n equal 2 to infinity rewritten. Okay, so that is my plan. Okay, so we'll start with this guy first. The 0th term, 4 a2 x to the 0, the 1 term. 3 times 2 is 6, times 2 is 12, a3 x to the first, plus the n equal to 1 term, 4 a1 x to the 1, the n equal to 0 term, 2a0 x to the 0, and the 1 term plus 2a1 x to the 1. And then I have plus summation n equal 2 to infinity, and have n minus 1 an plus 2 n plus 2 n plus 1 n plus 2 plus I have 4 n plus I have 2 an x to the n is equal to 0. Okay, well, my x to the 0 term has to be 0. Well, we'll start someplace else. We'll start with A0 is arbitrary. Why? Because I don't have an initial condition. A1 is arbitrary because I don't have an initial condition. Okay, and from the x to the 0 term, I know that, okay, so from the x to the 0 term, I know that 4a2 has to equal 2a0, which implies that a2 is equal to a0 divided by 2. And you guys are all yelling at me because there's a minus sign there and there's a minus sign there. Okay, so I put it in. x1, from the x1 term, we have that 12a3 plus 4a1 plus another 2a1 has to be 0. And from that we find that a3 has to be minus 1/2 a1. Okay, now we have a recurring formula. My recurring formula says that a n plus 2 is equal to, okay, so I've got minus n minus 1 plus 4n plus 2 an divided by 2 n plus 2 n plus 2 n plus 1. Isn't that nice? So there's an n squared, there's a minus n, so I've got minus n squared plus 3n plus 2 divided by 2 n plus 2 n plus 1. Okay, that seems reasonable. And there's an an standing there. Okay, and I look at it again and I say I've got minus, I factor this guy, n plus 2, n plus 1 divided by 2, n plus 2, n plus 1, an, and that comes out to a minus an over 2. So my recurring formula is minus an over 2. Isn't that lovely? So that being the case, a4 is going to be equal to, this is n plus 1, n plus 2, an plus 2, right? Yeah, an plus 2. So a4 is for all n greater than or equal to 2. So when n is equal to 2, I have 1/2 minus 1/2 a2. And a2 was minus 1/2, so I'm going to have 1/4 a0. And when n is equal to 3, I'm going to have a5 is equal to minus 1/2 a3, which is going to be 1/4 a1. Okay, that's probably enough to check our work. So we're going to declare we have a final answer, and the final answer is going to look like a0 plus a1x minus 1/2 a0x squared minus 1/2 a 1x cubed plus 1/4 a 0x to the 4th plus 1/4 a 1x to the 5th. Okay, so that's my final answer, and I need to check it. So y prime gets to be a 1 minus a 0x minus 3 halves a 1x squared plus a 0x cubed plus 5/4 a 1x to the 4th. And y double prime becomes minus a 0 minus 3a1x plus 3a0x squared plus 5a1x cubed. And because I need two of the double prime guys, I'm going to rewrite the double prime guy again. Double prime minus a0 minus 3a1x plus 3a0x squared plus 5a1x cubed. And when I take x squared of those guys and 2 of these guys and 4x of them and 2 of the answer, when I do that, I'm supposed to get 0. So now the issue is, can I do that? All right, so I have 2 a zeros. I have minus 2 a zeros. My a zeros go away. I'm looking at the x term. I have 2x1. I have 4 x1s for 6 x1s, a1x's, and then I have minus 6 a1x's. Boom, boom, boom. They go away. 0. And I'm looking at the x squared term. I have minus a0 minus 5a0 minus 5a0 minus 6a0 plus 6a0. The x squared term goes away. I'm looking at the x cubed term. Minus a1 minus a1 minus 6 a1s or minus 7 a1s. I have plus 10 minus 3. They go away too. And at that point I run out of things to check because I'd have to have more stuff in order to go further. So my answer checks. Everything's fine. And if you look in the back of the book, you'll see that you get the same thing too. Now I'm working problem number 6. X squared minus 1, y double prime minus 6x, y prime plus 12y is equal to 0. And I look at it and I see that I have an ordinary point at x is equal to 0. X is equal to 0. I have an ordinary point, so I can continue with what I'm doing. And so I've got x squared summation 0 to infinity n minus 1 an x to the n minus 2 minus summation n equals, this is 2 to infinity, 2 to infinity n minus 1 an x to the n minus 2 minus 6x summation n equal 1 to infinity and an x to the n minus 1 plus 12 summation n is equal to 0 to infinity. An x to the n is 0. Okay, bring in the x squared term. Summation n 2 to infinity n, that's an n, n minus 1 an x to the n minus summation n equal 2 to infinity n minus 1 an x to the n minus 2 minus summation n equal 1 to infinity 6 n x to the n plus summation n equals 0 to infinity 12 an x to the n is equal to 0. Okay, x to the n, x to the n, x to the n. So this guy I'm going to do a substitution in n equal n plus 2 so that everything's a to the n. Okay, summation, nope, wrong color. Summation n equal 2 to infinity n minus 1 an x to the n minus summation n equal 0 to infinity, because that used to be a 2, n plus 2 n plus 1 n plus 2 x to the n minus summation n equal 1 to infinity 6 n x to the n plus summation n equals 0 to infinity 12 n x to the n is equal to 0. Now, I'm going to have to start my summation someplace, so it's going to start at x is equal to 2, so we're going to remove n is equal to 0, n is equal to 1. We're going to remove n is equal to 1. If I could spell remove. And we're going to remove from this guy n is equal to 0, n is equal to 1. And when I get done, I'll have all my summations starting at n is equal to 2. Okay, so that's the plan. We're sticking with it. Okay, so we'll remove n is equal to 0. 2 times 1, a2. So minus 2, a2, x to the 0. We're removing the 1 term. 3 times 2 is 6, minus 6, a3, x to the 1. Removing the 1, n is equal to 1 term, minus 6 times 1, a1, x to the 1. Removing the 0 term, plus 12a0, x to the 0, plus the 1 term, 12a1, x to the 1. Then I'm going to have summation n is equal to 2 to infinity n minus 1 an minus n plus 2 n plus 1 an plus 2 minus 6 n plus 12 an x to the n is equal to 0. Okay, I look at the x0 term. Look at the x0 term, and I see minus 2a2, and I see 12a0. Now that has to equal 0, so that implies that a2 had better be 6a0. I look at the x1 term, and I have minus 6a3 minus 6a1 plus 12a1 is equal to 0. Okay, so I got that, which implies that a3 has to equal a1. Okay, we have a recurring formula. A n plus 2 equals. So I'm taking it from here, and I'm saying it's minus n minus 1 a n plus, well, this guy was minus. Okay, so we'll go with, put brackets there. Okay, so that one's minus, this guy's plus, this guy's minus, but they're both, no, they're both different. Okay, so plus 6n an plus 12 an divided by a minus sign, minus 2 plus n plus 2, n plus 2, n plus 1. Okay, and now we're going to go in and combine like terms and other such nonsense, some algebra stuff here, and say that an is going to be minus n squared minus 7n plus 12 an divided by minus n plus 2 n plus 1. And then we're going to factor some and hope for the best. an plus 2 is equal to, the minus signs go away, n minus 3, n minus 4 divided by n plus 2, n plus 1 for all n greater than or equal to 2. Okay. And a0 is arbitrary, and a1 is arbitrary. Well, I don't have initial conditions, so I don't know what they are, so they're both arbitrary. And I already figured out that a2 is equal to 6a0, and that a3 is equal to a1. So now we're going to look at n is equal to 2. We're looking for a4. Okay, so a is equal to 2. Looking for a4. And we have a4 is equal to minus 1 minus 2 divided by 4 times 3 times a2, which is going to be 6 times 6, 1 over 6, 1 over 6, a0, which is going to be a0. And then we're going to look at n is equal to 3 for a5, and we see that if we put a 3 in here, we get a 0, a5 is 0. Well, if a5 is 0, that means an is going to be 0 for all n greater than or equal to 5. So all the n's greater than or equal to 5 are going to have to be 0. Well, not really, but when I go to look at a4, it becomes 0 too. So 2 in a row becomes 0, and then everybody becomes 0. All right, so my answer becomes y, final answer, y is equal to a0 plus a1x plus 6a0 x squared plus a1x cubed plus a0 x4, and that's all there is. There ain't no more. Don't get any more than that. Y prime a1 plus 12 a0x plus 3 a1x squared plus 4 a0x cubed. Y double prime is equal to 12a0 plus 6 a1x plus 12a0x squared. And we're going to need two of them, so I'll write down that one more time. 12a0 plus 6a1x plus 12a0x squared. Oh well, that was a nice straight line, wasn't it? Okay, so I want x squared of the double prime guy. I want a minus 1 of the double prime guy, a minus 6x of the prime guy, and a 12 of the original formula. And when I get done, I better have 0. And if I don't have 0, I'm going to be very sad. So here's 12a0, there's 12a0, I have a 0. Here's 12a1x minus 6a1x minus another 6a1x. I have 0 again. Looking at the x squared term, I have 12 of them. X squared term, I've got 12 of them. I've got another 12 of them for 24, except they're negative. So they go away. Boom, boom, they go away. I've got plus 12 times 6 minus 12 times 6. They go away. My x cubed term, I have 12a1x cubes. I have another 6 for 18, and then I have minus 18. Boom, boom, boom. They go away. And I've got 12a0x squared, x to the fourth. X to the fourth. There's an x squared term sitting here. So I got 12. I got minus 24. I got another 12. That term goes away, so it's equal to 0. So the whole thing checks. And that's all that we really are here to do. All right, looking at number 10. Number 10. 3y double prime. So anyway, the last problem shows that I could have a finite series expansion solving these things too. Plus xy prime minus 4y is equal to 0. I look at my equation and I say x0 is an ordinary point again, so I'm happy about that. 3 summation n equal 2 to infinity n n minus 1 n x to the n minus 2. What we're going to do, we'll skip a step here and put that 3 on the inside. 3 on the inside. And then we'll say plus, and we'll do the same thing. N equal 1 to infinity. We'll bring the x in. N, a n, x to the n, minus summation n equals 0 to infinity for a n, x to the n is equal to 0. Alright, so we have to do a substitution in here. N is equal to n plus 2. When we get done, we'll have summation n equals 0 to infinity 3 n plus 2 n plus 1 a n plus 2 x to the n plus summation n equal 1 to infinity, n, a, n, x to the n, minus summation n equals 0 to infinity, 4a n x to the n is equal to 0. I have to get my indexing right, so I'm going to remove n is equal to 1. I'm going to remove n is equal to 1. No, I'm not. N is equal to 0. N is equal to 0. Much better. Okay, so that's what I'm going to do. So when n is equal to 0, I have 6a 2 x to the 0. When n is equal to 0, I have minus 4a 0 x to the 0, plus I have summation n equal 1 to infinity, and I've got 3 n plus 2 n plus 1 a n plus 2 plus n a n minus 4 a n x to the n is equal to 0. Okay. From the x is equal to 0 term, I have that, well, first of all, I have a0 is arbitrary. I have a1 is arbitrary. I don't have initial conditions yet. And from the x is equal to 0 term, I have that a2 is equal to 2 over 3 a1. Okay, I have a recurring formula. an plus 2 equals. Now here we have n minus 4. So I'm going to have a minus n minus 4 an divided by 3 n plus 2 n plus 1. Okay, and that's going to be for all n greater than or equal to 1, because my summation goes from n is equal to 1. Okay, that being the case, I'm going to look at n is equal to 1. What is a3? Okay, so a3. So I've got 1, that's a 3, it's a minus 3, it's a plus 3. So it'd be 3 times a1, which is arbitrary, divided by 1, 3 times 9 times 2, 18. So a3 is going to be a1 over 6. Okay, now I'm going to look at a4. When n is 2, a4 is going to equal, n is 2, 2 from minus 4, that's minus 2, so I have a plus 2 on the top. I have a 3 times 4 is 12, times 3 is 36, a2, and a2 is, so that'd be 2 over 36. a2 is 2 over 3, a0, so that's going to be a0 over 27. Okay, I'm going to look at n is equal to 3, which is going to be n5, and I'm going to have n is 3, so that's a 1, so it's going to be a3 over 60. 5 times 3 times 4, 60, which is going to be a1 over 360. Okay. And then we're going to look at n is equal to 4a6, and we see that that's equal to 0. When I put a 4 in my recurring formula, I get a 0. So at that point, I know that the rest of the even numbers, a, n, is going to be 0 for all n greater than or equal to 6 even. I still have odd ones, but I don't really need them right now because I think I have enough. So y of x becomes something. a0 plus a1x plus 3 over 2, 2 over 3, 2 over 3 a0, 2 over 3 a1. 2 over 3 a1 2 over 3 a0. That's a 0 there. Okay, 2 over 3 a0 plus a1 over 6 x squared. Oh, this is the x squared. X squared. This is x cubed plus 1 over 27 a0 x to the 4th plus 1 over 360 a1 x to the 5th. And y prime becomes a1 plus 4 over 3 a0x plus a1 over 2 x squared plus 4 over 27 a0x cubed plus a1 over, and 5 goes into that 72 times, x to the 4th. Y double prime. 4 over 3 a0 plus a1x plus 4 over 9 a0x squared plus, does 4 go into 72? Yes, it does. a1 divided by 18x cubed. And we need 3 of them and x of them and minus 4 of them. And when we get done, we want to have 0. Going back to the original problem on the top, yes, that's correct. Okay, I did that right. Okay, the a0 term, minus 4a0 plus 4a0, it goes away. The x term, minus 4a1 plus 4a1, it goes away. The x squared term, 12 thirds minus 12, minus 8, minus 8 thirds, 4 thirds, and 4 thirds, so it goes away. Plus 0. The x cubed term, minus 2 thirds, 1/2, and 1/6. So it goes away. And at that point I ran out of terms, but my problem checked. So that is good. Moving on to problem number 14. Y double prime plus xy is equal to 0. And I look again and I say, well, I've got an ordinary point, so I'm happy with everything. And I'm happy that the problem's a short problem, so I've got summation n is equal to 2 to infinity n plus n minus 1. N minus 1 an x to the n minus 2 plus summation n is equal to 0 to infinity, a n x to the n plus 1 is equal to 0. So now I say, well, what am I going to do with this? Well, could do many things. I'm going to do a substitution. N is equal to n plus 3. Then I'm going to be n plus 1 for my x's. So that's my plan. See what happens. Okay, summation n equals minus 1 to infinity, n plus 3, n plus 2, a n plus 3, x to the n plus 1, plus summation n is equal to 0 to infinity, a n x to the n minus plus 1 is equal to 0. Okay, I'm going to do a removal of the n minus 1 term. Removal n minus 1. Okay, I got 2, 1, a2. So I got 2, a2, x to the 1, x to the 0, x to the 0, plus summation n equals 0 to infinity, n plus 3, n plus 2, a n plus 3, plus a n x to the n plus 1 is equal to 0. Okay. Well, a0 and a1 are arbitrary because I don't know what they are. And a2 has to be 0. Why does a2 have to be 0? Because 2a2 has to be 0. So a2 has to be 0. So that's good. I have a recurring formula. Recurring formula. A n plus 3 is equal to minus a n divided by n plus 3, n plus 2, and I look at it as for all n greater than or equal to 0. So I look at n is equal to 0 to get a3 equals minus a0 divided by 3 times 2 is 6. Okay, and I look at n is equal to 1, and I get a4 is equal to minus a1 divided by 4 times 3, which is 12. And then I look at n is equal to 2, and I get a5 is equal to something times a2, which is going to be 0. So a5 is 0. I look at a6, n is equal to 3. Look at n is equal to 3. And I get a6 is equal to a3, which is minus a0 over 6, divided by 6 times 5, 6 times 5, which is 30, which is a0 divided by 180. And I have a minus sign sitting there, but the minus sign is sitting here, but the a3 is also minus, so this whole thing is minus, so it's really a plus sitting there. And then I look at a4, which is looking at A7, which is going to be minus A4, which is a minus A1 over 12, divided by 42, which is 6 times 7, 42, which is going to be A1 divided by 504. And if I look at n is equal to 5, I'm going to get an A8, which is going to be 0. Every third guy is going to be 0. Okay, well that's enough to check our work. So we have a final answer. Y of x is equal to A0 plus A1x plus, what's A2? A2 is 0. Okay. Minus A0 over 6x cubed minus A1 over 12x to the 4th. The A5 is 0 plus A0 over 180 x to the 6th plus A1 over 504 x to the 7. Okay, and then we need the first derivative. A1 minus A0 over 2x squared minus A1 over 3x cubed plus A0 over 30x to the 5th plus A1 over 72 x to the 6th. Y double prime. That guy goes away. Minus A0x minus A0x minus A1x squared plus A0 over 6x to the 4th plus A1 x to the 5th over 12. Right? I need 1 of that guy. I need x of this guy. And when I get done, I better have 0. I don't need any of the first derivative guy. Okay, that's our plan. I have plus and minus 0. I have plus and minus 0. I've got minus to the 4th power plus to the 4th power 0. I got minus to the 5th power plus to the 5th power 0. Check. Okay, so my problem checks, and that problem is complete. And with that, we're done with section 8-2.